Greetings, fellow night owls. This is Dr. Nighttime, and I'd like to begin a series of videos where I work through some of the written answer problems from previous LTAM exams. I would advise that students who are studying actually put more effort into studying previous written answer questions for a couple of reasons. One, the majority of the exam is written answer. And two, the written answer questions themselves are harder, so if you put most of your effort into studying the multiple choice, you'll find yourself underprepared for a lot of the written answer questions. Anyway, let me begin with the most recent written answer, most recent LTAM exam, question number 1. So 9 points. Steve, a 45-year-old, was hit by a truck belonging to XYZ. Steve suffered permanent injuries and, as a result of the lawsuit, was awarded a non-reviewable structured settlement. The settlement will provide Steve with the following payments: a death benefit of $100,000 payable at the moment of death if Steve dies before age 65, a survival benefit of $200,000 payable on Steve's 65th birthday, and a monthly life annuity due of $4,000 per month. XYZ decides to purchase the structured settlement from the JAB insurance company. JAB uses the following assumptions to calculate the present value of the benefits. Steve's force of mortality at age X at least 45 is mu sub X, where that's equal to the standard ultimate life table's mu sub X plus an additional 0.02. The force of interest is 0.045. And the two-term Woolhouse formula is used to calculate mortality and continuous annuity values and to calculate insurance functions from the annuity values. You're also given that based on those assumptions above, A double dot 45 equals 14.4893 and A double dot 45 colon angle 20 equals 11.4411. So part A is actually the hardest part. It says, show that the actuarial present value of the survival benefit is 52,050 to the nearest 10. You should calculate your value to the nearest 0.1. And so what we have is that the sorry, I forgot to prime that. Yeah, that the survival benefit is equal to e to the negative 20 delta, right? That's just the discount factor, times probability that the person survives 20 years, px20, or I guess p4520, since we know that Steve is 45 years old. All right, px20 equals, this should be a familiar formula, e to the negative antiderivative of the hazard function. Okay, we know that the hazard function is equal to the force of mortality from standard ultimate life tables plus 0.02. All right, we can break up that antiderivative into the sum of two antiderivatives. The antiderivative of the standard ultimate life table mortality, that one, we'll just treat that separately. It's going to be whatever it's going to be. Right? And then we're adding an additional 0.40, right? 0.02 integrated over a width of 20 is 0.40. We're adding that. And when we add two things inside of an exponent, we can just multiply the exponentials. And what that means is, if you'll notice, e to the antiderivative from 0 to 20 of the standard ultimate life table function, right, standard ultimate life table mortality, that's just going to be the standard probability of a 45-year-old surviving 20 years. And we just need to multiply that by the remaining e to the negative 0.4. So to find that standard survival probability, we look back at our standard ultimate life table. It says that we can assume out of 100,000 people who made it to age 20 at the start of the table, 99,034 of them made it to age 45, 94,580 of them make it to age 65, just rounding to the nearest whole number. We just divide those two numbers, we get a 95.5% chance of Steve surviving to age 65. Multiply that by the time discount, we get 0.64017. Again, I forgot to prime this, but the survival benefit is going to be e to the 0.9, right? That is 20 years worth of time discount times 0.64017, which ends up being 0.26027, which I also annotate here. This is going to be E4520. And that's a number that's going to come up a bit in later parts of the problem. So we're going to be using that. And so the actual survival benefit, I was calculating it previously based on the assumption of a $1 benefit. This is a $200,000 benefit. So we just multiply by $200,000 to get 52,054.96. I know they said to the round to the nearest 0.1, but that was going to get me 55.0, and people would say, well, why do you round down instead of up? This is why you end up rounding down to 52,050 rather than up to 52,060. Just wanted to show that one extra decimal place to get that in there. All right. Next part. Calculate the actuarial present value of the monthly annuity due. And here's where we start using Woolhouse's formula. Woolhouse's formula I've generally seen presented really badly. They just give you a formula saying, here, try to remember this without significant explanation. I'm going to hand wave the beginning of the explanation here so that you'll actually have some way to actually make sense of it. So what I've got here, this black curve here, that represents the endowment function of a 45-year-old surviving some number of years. Assume that the blue lines are, those represent payments per year. So notice that would assume that you evaluate, that you make payments annually. So you make one payment for the whole year. That's only based on your surviving to the beginning. Then 1 year just based on your surviving. Then one payment the next year just based on your surviving that year, etc., year to year. The green payment is kind of assuming there are only 2 months in a year, just because it becomes a little too much of an eyesore for me to have 12 of these every year. But that's going to be the monthly or monthly payments, where M is 12. We'll just make an adjustment when, where M is 2 in the diagram. Oh, we can make an adjustment for any M that we need. And what you do is, for the two-term approximation, you assume that this black curve, we approximate it with the standard trapezoidal rule that you might have seen in Calculus 2, where you just connect the endpoints. So this little tiny piece up here that gets cut off is going to be 1/2 of the width, which is 1 year, times the height, which is the endowment at the beginning of the year minus endowment at the end of the year. Then you do that for the next year and the next year. And when you do 1/2 of beginning minus end plus beginning of the next year, which is the same as the end of the previous year, minus the next one, you get a telescoping sum. So it just telescopes down to minus 1/2 E45N, where N is however many years you want to look into the future. In the special case where you're looking at something infinitely far into the future, E45N is 0 because, first of all, nobody lives forever. Second of all, with any sort of interest, the purchasing power would attenuate down to 0. And so this just becomes a 0 here. That's the version that shows up in the tables, which means they tend to like to ask more complicated versions than that because they give you that simple version in the tables. So you just have to know to subtract out the E45N here when necessary. And so when we just compare those for various frequencies, so if you're just doing annual frequency, you get this formula. Monthly frequency, you get that formula. Since they both have to be approximately equal to the same thing, we can set them equal to each other to get A45 colon angle N compounded monthly equals A45 A.45 colon angle N minus 1/2 of 1 minus E45N plus 1/2M, the compounding frequency, times 1 minus E45N. If this isn't quite intuitive, I will be uploading a video relatively shortly that goes in more detail as that explains the Woolhouse formula in more detail and where it comes from, but this is the formula you'd end up needing to know. So for the monthly annuity due, this is a whole life, so we just subtract 0. Just going to take 48,000 times this 14.4893 that they give us, minus 1/2 of 1, plus 1/24 of 1, 24 because it's 2 times m is 12 because it's monthly, and that gets us 673,486. So next we have to calculate the actuarial present value of the death benefit. So since the death benefit is continuously evaluated, it's payable at the moment of death, we need to use continuous functions. And so since it's a 20-year term insurance, we pretend that's a whole life insurance, or sorry, we pretend it's the 20-year endowment insurance rather, minus the endowment component. We already know how much this endowment component is. We calculated it in the previous problem. And we use our formula relating endowment insurance to annuities. We say it's going to be 1 minus A bar 45 colon angle 20 times the discount rate. And then we just use the Woolhouse approximation again. We can even just use this line on its own right here. And that'll get us that it's A double dot 45 colon angle 20 minus 1/2 of 1 minus E 4520. All times delta minus the endowment, E 4520. We crunch those numbers in, and we should get 0.24152. Okay, so that was the hardest part, as I mentioned. Part 2 is somewhat easier. It says, determine the reserve that JAB should hold at the end of 20 years, assuming Steve is alive at the time. And since you're looking at the end of 20 years, the convention is to assume that any payments due at 20 years have already been made. Anything that the company is owed has not been made. The assumption behind that being, well, if you know you have to pay by the end of 20 years, you need to make sure you've gotten it out. The check has to already be out, whereas it can take a little longer for checks to come in. So, the only thing left after 20 years, the death benefit has expired, the survival benefit has already been paid, and so now it's just this person is alive and he's 65 years old. You assume, all right, you've got this $4,000 a month or $48,000 a year monthly annuity, and so you just have to look at A double dot 65 compounded monthly. So you'll notice that's going to be e to the 0.90, that's 20 years of discount, of A double dot 45 compounded monthly minus A double dot 45 colon angle 20 compounded monthly. That's just everything for the full year, for everything starting from when you're 45, minus the amount that was already accounted for in those first 20 years. So using Woolhouse formula again for the full time, you'll have A double dot 45 minus 1/2 1 minus 0 for that. And to evaluate it monthly, to evaluate it with a 20-year term, you just say it's going to be the amount with the 20-year term minus 1/2 of 1 minus E 4520, as we showed previously. Crunch those numbers together. You get that one of them is 13.9893, the other is 11.0712. We take the difference, we multiply it by the discount factor, because remember, the values with the 45s in them they're saying current value, looking at something that's going to be happening 20 years in the future. So the reserve you need to have 20 years into the future better account for that interest factor. All right, we crunch the numbers there. We get 7.177. Multiply that by the 48,000 a year, and we get 344,509. And lastly, and this part, I feel like I'm missing something on one of these, or there might have been a typo that was corrected in the exam room itself, but because I'm just looking at it a couple months later, I wouldn't know about that. So they say they recalculate the actuarial present value of the settlement benefits under the following assumptions. Mortality follows the standard ultimate life table with the addition of, this time, only 0.01 to the force of mortality. So notice that the mortality is lower. You're likely to live longer than you did under the previous assumption. And force of interest is now 0.055. Previously, it was 0.045. So money declines, or the purchasing power of money decreases more rapidly. So for part one, without further calculation, state whether the actuarial present value of the monthly annuity due would increase, decrease, or stay the same. And this is where I feel like I'm missing something, because mortality decreased. You're likely to live longer. That would mean that if it were only that factor, then the annuity due would be worth more, right? Because you're living longer. You're likely to need to make payments for longer. But interest went up. That means that subsequent payments, obviously the first payment is worth $4,000 because it's right now. Future payments will be worth less than they would be. You have these two competing factors. Trying to tell whether the net effect is going to increase or decrease when you have two competing factors, that's hard to figure out without calculation. If I'm wrong, please let me know in the comments. I'm going to feel like a huge knucklehead for missing whatever this is. I'm probably missing something. I'm probably overlooking something. I'm going to feel like a knucklehead when I read whatever it is. Feel free to leave your comment off with, hey, knucklehead, here's what you missed. Anyway, part two is considerably simpler. Without further calculation, state whether the actuarial present value of the death benefit would increase, decrease, or stay the same. And so this is more straightforward. Right? You live longer, therefore you're less likely to require a death benefit. And if you receive a death benefit, since it's going to be in the future, that's going to be worth less because of the increased interest. So on both accounts, the death benefit's value would decrease. So I seem to be missing something on this part C1 here, but hopefully you found the rest of this useful. And as always, if you're interested in arranging private sessions, feel free to check the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.